This video is about parametric surfaces. We're going to discuss graphing parametric surfaces. I'll show you a couple of examples. We'll show you how to find a parametric representation of a surface given by z equals a function of two variables, x and y. I'll show you how to find the normal vector of a parametric surface and then use that normal vector to construct the equation of the tangent plane. And then I will show you how to find the surface area of a surface given parametrically. So let's briefly talk about parametric curves and then talk about how that we extend that to come up with equations for parametric surfaces. So let's say we have y as a function of x in the xy plane. Typically this is how we represented curves before this course. Every x is associated with one y value. Sometimes we went the other way around. We had x as a function of y instead of y being a function of x. But every x maps to a particular y value. And I've got an x-axis and a y-axis here, and that's all we see. We see that relationship. Now, when we started this class, and at the very end of Calculus 2, you started studying parametric equations of curves. So we were able to come up with plane curves in 2D by tying x and y together with a third variable. That third variable is called t. That's also known as the parameter. And so as t went through some range of values, we would get a curve that looks like this, potentially, in the xy plane. Now notice that there's no t-axis here, but there is some interval of t values. There's like some real line of t values. And for a particular t, for that particular t value, we point to a particular location. And over here as well, t is some number on a real axis that's not shown here. And for a particular value of t, that r of t points to a particular location. Now again, there's no t-axis, but every t is associated with an x and a y, and as t increases, we trace out a curve. Similarly, when we look at space curves, as t increases, we're tracing out this curve. We've got some like abstract t-axis somewhere, and for every t value in the domain, we map to a point in the plane or a point in space. Now, these are called usually piecewise smooth parameterizations of these curves. That's what we've been looking for in the last couple of sections. We could have plane curves or space curves. We could technically have n-dimensional curves. The components of these vector valued functions are called the parametric equations of the curve. Now that's how we had parametric representations of curves. So we're tying a location, x and y, to a particular t value, and there's no t-axis. But as t moves through a range of values, we trace out that curve. Similarly, we do the same thing in three-dimensional space. And I've drawn in the vectors r of t here. R of t starts at the origin and points to a particular location. All right, now let's extend this idea to parametric surfaces and surfaces in general. So before we discuss this idea of a parametric surface, this is how we represented surfaces typically. We'd say every xy in the domain of this function f of xy maps to a particular z value. And then as x and y move through all of those points in that domain region, we get z values on our surface. So we could represent the surface this way. Z equals f of xy. We also said we could represent it this way. We could subtract that f of xy from both sides and have f of xy and z equals 0. That's another way to represent that surface. We can think of it as a level surface of this function of three variables, capital F of x, y, z. In this section, we're talking about representing surfaces in another way. With parametrically defined surfaces, we've got something that looks like this. Notice the similarity between this form and this form. It's a vector valued function, except instead of accepting a single real number as an input, the input values are ordered pairs in the UV plane. Now over here, we were taking a real number t and we're mapping it to a particular location. Now we're taking an ordered pair of real numbers from the UV plane. So maybe this is U and this is V and this is our domain. And every UV in here maps to a particular location over here. So that UV pair maps to that location. Now we can also represent this by a vector. Every UV in this domain gives you an X and a Y and a Z. Now, as if U is held constant, let's say, and V moves through a range of values. So let's say we have R evaluated at U naught. So this is just U equals U naught. Now I've got X of U naught and V, Y of U naught and V, and Z of U naught and V. If U naught is a constant, I've just replaced it with a number. Now R is a function of V only. So I got X of V, Y of V, and Z of V. That looks just like this, except instead of using a T, I've got a V. But the principle, the idea is exactly the same. So if U is equal to a constant, what we end up with over here is just a curve, a curve that lies on our surface. Maybe that curve looks like this. So this is R of U naught and V. Not V naught, just R of U naught and V, just for example. And let's say this location is X of U naught, V naught, Y of U naught, V naught, Z of U naught, V naught. So that's R of U naught, V naught pointing to that location there. Okay. So R of U naught and V comes from letting U equal U naught and then letting V go through a range of values, and then we get a curve on the surface like that. Well, I could do the same thing by holding V equal to a constant. So I'll have R of U and V naught. So I've got X of U and V naught, Y of U and V naught, and Z of U and V naught. So now R is a function of U only. Instead of being a function of V only, it's a function of U only because I've replaced all the V's with V naughts. So what that does for us is it gives us a different curve on our surface. Maybe that looks like this. So that might be R of U and V naught. So we're on the line over here, V equals V naught, and we're letting U go through a range of values, and that gives us this curve. And as we continue to do that, so V goes through a range of values, and then U goes through a range of values. Because we've got two variables, instead of getting a curve in three-dimensional space, we get a surface in three-dimensional space. So this is just another way of representing a surface. We could have Z as a function of X and Y. We could take this equation and move all the variables to one side, so we could have f of x, y, and z equals z minus little f of x, y, or we could do it the other way around. You know, f of x, y minus z. Either one of those would be fine, and those would both be rectangular equations for the surface. they're just equations involving x, y, and z. Over here, we're doing something a little different, which is much more like these two parametric representations of curves. There is no UV plane pictured here. But when we have a parametric representation of a surface, we're saying, okay, for some UV in some UV plane, where the domain of R lies in this UV plane over here, for every UV pair in that domain, we want to associate that with a point. X of U and V, Y of U and V, Z of U and V. And as U goes through a range of values and V goes through a range of values, we'll get the whole surface. So that's the idea behind parametric surfaces. Let's practice graphing some parametric surfaces now. So here's our first example. We're asked to find the rectangular equation for the surface by eliminating the parameters U and V. And then we're asked to identify the surface and sketch its graph. Okay, we're going to graph this in pretty much the same way that we graphed parametric curves. Over here, when we were in this chapter on vector valued functions, in order to sketch these curves, often what we did was we set x equal to x of t, y equal to y of t. We solve one of those equations for t and then substitute into the other one. And then we'll get y as a function of x, or x is a function of y. That's the rectangular equation of the curve. Space curves were a little more challenging. Often we would get a relationship between x, y, and z, and that would tell us a surface that our curve was lying on. And then once we had a surface that the curve was lying on, we could let t go through a range of values and imagine what would happen to that curve as it lied on that surface as t increased. And there was often a lot of spiraling. That was just typical for the examples that we have in our book, or the examples that were easy for us to graph. Okay, so now we're going to do the same thing here. We're trying to get rid of the parameters u and v so that we have a rectangular equation of the surface. Remember, a rectangular equation is just an equation involving x, y, and z describing your surface. So this is x of u and v. This component here is y of u and v. And this component is z of u and v. And we're told we've got this range of v values and this range of u values. So the domain of this function in the uv plane, u goes from 0 to 4, v goes from 0 to pi, now every point u and v in this little rectangle is going to correspond to a point on a surface in three-dimensional space. So every uv over here maps to a point over there. R of u and v does that. R of u and v takes each of these points and it maps them to a particular location in three-dimensional space. Our goal is to graph that surface by finding a relationship between x, y, and z that doesn't involve u and v. We just want the equation of the surface without any u's and v's in it. So the best way to do this, or I find the easiest way to do this, is to state the parametric equations of the surface, but don't include that dependence on u and v. I think it's sort of obvious that x depends on u and v, y depends on u and v, and z depends on u and v. So that's the first thing we do. Or what I wrote state the rectangular equations. what I'm doing right now is I'm stating the parametric equations for the surface. And now your goal is to eliminate the parameters u and v, usually one at a time. Now, the first thing I notice is that y is equal to u and x has a u in it and z has a u in it. So if you want, you could immediately substitute. Trying to get rid of the u's, I see that x is equal to y times cosine of v, and z is equal to y times sine of v, because y is equal to u. So I've just replaced that u with y, and I've replaced that u with y, and we're here. And that's nice, because that gets rid of the u in the equations for x and z. Now, another thing I notice is that I've got these two trig functions with the same angle. I've got sine of v and cosine of v, and that is very helpful because I know that sine squared plus cosine squared, when the angles are the same, always gives us 1. So we would take these and solve for cosine of v, and take this one and solve for sine of v. And the reason we do that is because we know that cosine squared plus sine squared is 1. So we can replace cosine in that identity with x over y. We can replace sine in that identity with z over y and set it equal to 1. We've got cosine squared plus sine squared equals 1. And I'm replacing cosine of v with x over y. I'm replacing sine of v with z over y. And then let's simplify that equation. And that's nice. That's a rectangular equation. It involves x and y and z only. So I've got x squared over y squared plus z squared over y squared equals 1. And I see that I've got a y squared in the denominator. So I'd like to multiply, both sides by y squared. Should be a z. So x squared plus z squared equals y squared. Or if I subtract y squared from both sides, I see this. Okay, so what did I do? The first thing I did was I stated those parametric equations of the surface, and then my goal was to eliminate the parameters u and v. Okay, so I replaced my u's with y's because I was told that those are the same. And then I used a trig identity to get rid of the cosine and sine. Anytime you have cosine and sine of the same angle, you're probably going to use this Pythagorean identity to get rid of it. So you solve for cosine of v, you solve for sine of v, you substitute, and that gets rid of the v's. Now you've got this rectangular equation involving x and y. So once you get that rectangular equation, then you simplify this equation until it looks like one of the equations that you're familiar with. And the whole idea is that when you're done, you'll end up with a surface that you've studied before. Hopefully it's a surface that you recognize. And this is one that we recognize. X, Y, and Z are all squared. These two are positive, that one's negative. There's a 0 on the right-hand side. So this is the equation of an elliptic cone. It's actually a circular cone. It opens in the direction of the y-axis. And that point in the very middle of the cone is at 0, 0, 0. We've been calling that the center. Okay, so that is enough to graph our surface. Now, it turns out we don't get the whole cone, we only get part of the cone. In order to figure out which part of the cone, we need to look at these requirements on the parameter over here, the two parameters, excuse me, over here. Well, this one is the most telling, I think. U goes between 0 and 4, and y is equal to u. So that means that y must range from 0 to 4, because y and u are the same thing. Okay, so I've got a cone. Y ranges from 0 to 4. It opens on the y-axis, so it's generally going to look like that. But look at this. V ranges from 0 to pi. So what does that do? If V went from 0 to 2 pi, that means cosine would take on all of its values and sine would take on all of its values. But that's not what happens. We only get half of the values. So in order to figure out the range of values for x, I'm going to look at the cosine of V curve in another plane where there's the V axis. Here's cosine. That's what the cosine function looks like. I don't even know what letter to use. I'm just going to write cosine of V. Well, the cosine function, if V goes from 0 to pi, takes on all of the values between -1 and 1. So x is going to take on all the values between negative u and u. I'm taking this inequality and I'm multiplying it by u. So x goes from negative u to u. Okay. And then similarly, let's look at the sine curve. Sine looks like this. But if we're on the interval from 0 to pi, sine doesn't take on all of its values. Sine just goes from 0 to 1 on that interval. Just on the interval from 0 to pi. And if sine goes from 0 to 1, that means z, if I multiply this inequality by u, that means z goes from 0 to u. So z is always greater than or equal to 0. So what does that mean? Well, it means that whenever we're getting that cone, like this right here looks like this. It opens on the y-axis. That's the general shape. Now that's not what we get here. We get something very close. We get a cone that opens on the y-axis, but it's only on that positive y-axis because u is between 0 and 4, which implies that y is between 0 and 4. And then this range of values tells us that z goes from 0 to u, or remember what z is, or u is y. So z goes from 0 to y, and x goes from negative y to y. What does that mean? That means we don't get the whole cone, we just get that top half of the cone. We get the part of the cone that lies above the xy plane. So it's going to look like this. When y is 4, x is going to go from -4 to 4, and z is going to go all the way up to 4. And so we've got a cone Actually, I'll just draw it this way. It's just a cone. Whoops, it's supposed to be a straight edge. But we only get part of it, the part that lies above the XY plane. It's not the best picture, but I hope you understand what I'm trying to do there. The whole cone would go below and then it would come back up. We just get that part that's lying above the plane. Okay. Okay. All right, let's do another one. This time we're not given any range of values for u or v, but we see a bunch of trig functions again. So we're going to do the same thing that we did last time. This is our x, that's our y, and that's our z. So x is 3 cosine of v cosine of u. Y is 3 cosine of v sine of u. And z is 5 sine of v. Now right away, I notice that I've got a cosine of u and a sine of u right here. So I can take each of these equations and solve for cosine and sine, and then use the fact that cosine squared plus sine squared is 1. Or rather than doing that algebraic manipulation, which leads to fractions, I could just take the x and the y and square them and add them together, and that should get rid of the cosine and sine. Let me show you what I mean. Cosine and sine of u anyway. Those cosines of v are still going to be there. So I replace the x with 3 cosine of v cosine of u. I replace the y with 3 cosine of v sine of u. Oops, cosine of u. And then we square them. We've got 3 factors each, so 3 squared is 9. Cosine of v squared is cosine squared v, and then this is cosine squared u. We have 9 cosine squared v sine squared u. And then, as always, we look at these two guys, we say, what do they have in common? They both have a cosine, or 9 cosine squared v in common. So we'll factor out that 9 cosine squared v. And then we're left with cosine squared u plus sine squared u. And cosine squared u plus sine squared u is 1. That's nice. Now we've got x squared plus y squared equals 9 cosine squared v. All right, so that's x squared plus y squared. It still has a v in it, unfortunately. And our equation for z also has a v in it. It has that sine of v in it. But I know that sine squared plus cosine squared, when the angles are the same, is 1. So I should be able to relate this z to this x squared and y squared by using the identity that cosine squared v plus sine squared v is 1. So what I'll do to do that, to use that identity, is I'll get cosine squared v by itself by dividing both sides by 9. And then I'll take this equation for z, and I'll divide both sides by 5. Now if I take that and I square it, I get this. That side squared equals sine squared. And this equals cosine squared. And we know that when we put those two pieces together, cosine squared plus sine squared is 1. Well, in our case, cosine squared v turns out to be x squared over 9 plus y squared over 9. And sine squared v ends up being z squared over 25. So now we've got an equation involving x, y, and z. And then we think back to that first chapter on quadric surfaces, and we try to remember, what does that graph look like? Well, the x, the y, and the z are all squared. All three terms are positive, and the right-hand side is a 1. So this is an ellipsoid centered at the origin. And I know it's centered at the origin because I'm not subtracting anything from the x, the y, or the z. That's not 0, 0, it's 0, 0, 0. And we're going plus or minus 3 units in the x direction because there's a 3 squared under the x. We go plus or minus 3 units in the y direction because there's a 3 squared under the y. And we go plus or minus 5 units in the z direction because there's a 5 squared under the z. So our ellipsoid looks like this. So it looks like we've got a circle in the xy plane. It looks sort of elliptical because it's on an angle. And then we go up and down 5 units in the z direction. Yeah, this is not the best picture. Okay, it's pretty bad. So that's rough. When in doubt, just say, this is an ellipsoid centered at the origin. And make sure you label that as 5 and -5, 3, -3, 3, 3, and -3. And then it doesn't have to be perfect, it just has to be roughly reminiscent of an ellipsoid. Okay. So that is how we graph parametric surfaces. Now, if I want to find a parametric representation of a surface given by z equals f of xy, it's actually pretty simple. Let's use the bottom of this sheet of paper here. It actually is simple to find a parametric representation of any surface given as a function of 2 variables. So let's say we have z as a function of x and y. Then we can let x equal u and y equal v. Then in that case, z is f evaluated at u and v. So our parametric representation would be x equals u, y equals v, z equals f of u and v. It's very simple. So just as a very brief example, if z is equal to, let's just say 4x minus 3y plus 2, so it's just a plane, then the one parametric representation of that plane can be given this way. Let x equal u, let y equal v, and then in this equation, you replace x with u and you replace y with v, and that's going to give you the equation for z. So we'll have 4 times x, which is u, minus 3 times y, which is replaced with v, plus 2, and that's our parametric representation. Now we could generalize this idea. Z doesn't have to be a function of 2 variables. It could just as easily be x as a function of 2 variables. So if x is a function of y and z, then you can let y equal u and let z equal v. Then x will be f of u and v. So you get this. I mean, it's pretty simple. So let's say someone gave you x equals z squared plus y squared. So we've got that elliptic paraboloid that opens on the positive x-axis. Well, then you could replace y with u and replace z with v, and then x would be v squared plus u squared, or we could change the order, u squared plus v squared. We'd have that. And of course, this works if y is a function of two variables as well. So very simple way to get a parametric representation of any surface written this way. And I'll show you the last one, even though probably don't need it. If y is a function of x and z, we can replace x with u and z with v, then y will be f of u and v. So r is given by x equals u, z equals v, y equals f of u and v. It's exactly the same as that first one. We just change our perspective a little bit. Here we're thinking of z as a function of two variables. Here we're thinking of x as a function of two variables. And there we're thinking of y as a function of two variables. Okay, that was easy. Now let's think about how we would find the normal vector to a parametric surface and then come up with the equation of a tangent plane. Now let's say the domain of our parametric surface given by r of u and v with components x of u and v, y of u and v, z of u and v looks something like this. You've got some region in the UV plane. And that's your domain. Maybe we're going to use the label D for this. We've been using R for a region in the XY plane. We'll call D this region in the UV plane. Well, if I draw a little grid over this region D, so I split the U direction into a bunch of subdivisions of equal width. Those are supposed to be equal. That's delta U. And then we'll do the same thing in the V direction. That's delta V. So we've got a little square that looks like this. On each of these lines, if that's where U is being held equal to a constant, we end up with a different curve, just like we talked about before. If I'm on a line like this, let's say we say U is equal to U naught, that's right here on this line. Well, that's going to represent a curve on the surface, R of U naught and V. So X is replaced with X of U naught and V, Y is replaced with Y of U naught and V, and so on. We just substitute in U naught. Now this is a function of V only. Excuse me. If U is equal to U naught, we might get a curve that looks like this. This is R of U naught and V. As v goes through a range of values, we get this curve on the surface. Similarly, if v is equal to a constant, oops, I think this is the pink highlighter that I need to throw away. It always sort of gets me. That's v equals v naught. When v is equal to v naught, that corresponds to a curve on the surface. Oops, it's u and v naught. And if you're saying to yourself, why is it a curve on the surface again? It's a very good question. It's a curve on the surface because I've replaced v with v naught, and now r is a function of a single variable. R is just r of u. So it's kind of like r of t. We've got x is a function of u, y is a function of u, z is a function of u. And as u takes on a range of values, well, we just end up tracing out a curve on the surface. So here is r of u naught and v. Maybe this is a curve. R of u and v naught. And then they intersect here at this location. That point there is r of u naught and v naught. So it has coordinates x of u naught and v naught, y of u naught and v naught, and z of u naught and v naught. So you've got that point right there. The question is, what is the normal vector to the surface right there? If I draw a little tangent plane, what's the normal vector to that tangent plane? Well, I can find it as long as I can find two tangent lines in this plane. Well, that's actually pretty easy. I know that r of u naught and v passes through this point, and I know that r of u and v naught passes through this point. So when I have this function, r of u and v naught, I can take its partial derivative with respect to u. So as u changes, we go a little bit on the surface, and that's going to give us a tangent vector right there. So I'm sorry, I got distracted. A student was texting me. If I take the instantaneous rate of change of r with respect to u at u naught and v naught, well, that's going to give me a tangent vector. So that is the partial of u, or partial of r with respect to u, evaluated at u naught and v naught. And so the way you find that is the same way that you found the derivative of r with respect to t. You just take the derivative term by term, but now since this is a function of two variables, we have to take partial derivatives. So you have the partial of x with respect to u, the partial of y with respect to u, and the partial of z with respect to u. And we evaluate all of these at u naught v naught. And that's going to give us a little tangent vector there. And then if I want, excuse me, another tangent, I'll do the same thing over here. As v increases, we trace out this curve. So if I take the derivative of r with respect to v, the partial derivative of r with respect to v, that's going to give me a tangent line at u naught v naught as well. So I take the partial of r with respect to v, giving us a little tangent vector in that direction. And again, the way you compute this partial derivative is just, I said term by term, but it's actually component by component because we're dealing with vectors, aren't we? So take the partial of x with respect to v, the partial of y with respect to v, and the partial of z with respect to v. And we evaluate all of these at u naught, v naught. Now, if I want the normal vector here, I need a vector that's perpendicular to the plane that contains both of these tangent vectors. Now, remember when we studied cross product at the very beginning of the course, we said that if I've got a plane containing u and v, and these u's and v's are different from these u's and v's, sorry, we're using the same notation. If I take the cross product of those two vectors, one of those vectors is pointing up from that plane, and the other one points down. By the right-hand rule, it looks like u cross v points up, and v cross u, that's the one that goes the other way, it goes down. So if I want the normal vector to the plane that contains those two vectors, and these are two vectors in that plane, all I have to do is take the cross product of those two. So a normal vector is the partial of r with respect to u, which can be notated that way with that subscript notation, crossed with the partial of r with respect to v. Now that is not a unit vector. If we want it to be a unit vector, we'd have to divide by the length. And of course, if we want this to have components that are non-variable components, we need to evaluate this at u naught, v naught. It's going to give you a vector with components a, b, and c, and that's the normal vector there. So that's the normal vector to the surface at that point. And any normal vector to the surface at a point is also the normal vector to the tangent plane, or a normal vector to the tangent plane, or for the tangent plane. At the location x of u naught, v naught, y of u naught, v naught, z of u naught, v naught. Remember, x, y, and z give you location. And u naught, v naught, those are the two values of the parameter in this uv plane that point us to that location. Okay, so let's use this formula for a particular surface. Let's say we've got a surface that looks like this. R of u and v is u times I hat plus v times j hat plus 4 minus u squared minus v squared times k hat. Now notice right away that this corresponds to a particular surface. If x is u and y is v and z is 4 minus u squared minus v squared, it's pretty simple to eliminate the parameters u and v. You just replace x with u here, you replace y with v, or you replace u with x here, you replace v with y here, and what you get is z equals 4 minus x squared minus y squared. So we've got an elliptic paraboloid facing down. And when x and y are both 0, z is 4. Now there are no limitations on x and y, but I'm just going to sketch it this way. So that's roughly what we've got there. Okay, now let's say somebody asks you to find the tangent plane. So let's say someone asks you to find the normal vector at x equals 1, y equals 1, and then z would have to equal 2. and then find the tangent plane at that location. Find the equation of the tangent plane at that location. Now we could just use this version of the surface. I know that would probably be easier and more comfortable for us, but we want to practice finding the normal vector using this formula on the other page, because sometimes we don't actually know what the surface looks like, and we just have this parametric representation. Even if I can't graph it, even if I don't know what it looks like, I know that a normal vector to the surface is given by this cross product evaluated at u naught v naught. So first, let's identify u naught and v naught. They're giving us x, y, and z. So they're saying x of u naught and v naught, which is u, well, and evaluated at u naught, that's going to be u naught. And the x value is equal to 1. Y of u naught and v naught, that's v naught, that's equal to 1. And z of u naught and v naught, that's 4 minus u naught squared minus v naught squared. That's equal to 2. Well, because of this equation, it's very simple. U naught must be 1 and v naught must be 1. And if u naught and v naught are 1, we get 4 minus 1 is 2. So that all checks out. So you just set the x, y, and z equal to this x, y, and z, and you infer the value of u naught and v naught, which in this case was very simple. And now we need to compute those two partial derivatives. Let me write down that step that we just did. We set x, y, and z equal to 1, 1, and 2 respectively. And then we solve for u naught and v naught. And usually there's one equation that's really obvious that sort of tells you what u naught or v naught has to be. In this case, there were 2 of them. Occasionally it requires a little bit more algebra, but most of the time it's pretty straightforward like this. So you find out that u naught and v naught have to be 1. Once we do that, we want to compute those two partial derivatives so that we can find their cross product and evaluate it at 1, 1. So we want to compute the partial of r with respect to u, which can also be written in subscript notation that way, and the partial of r with respect to v, which can be written in subscript notation that way. So we're taking the partial with respect to u of this vector valued function component by component. Of course, the partial of u with respect to u is 1. There's no u there, so that's 0. Partial of this guy with respect to u is negative 2u. Do the same thing with respect to v. So you have a 0 there because there are no v's in that. Then we have a 1, and then we have a negative 2v. And for the normal vector, we need to take those two vectors and take their cross product. You can also evaluate this at u naught and v naught first. I think that would be simpler. So we computed those two partials, and then we want to evaluate them at u naught v naught. So we have r, partial of r with respect to u at 1, 1. That's 1, 0, negative 2. And then the partial of r with respect to v at 1, 1. If v is 1, we get 0, 1, negative 2. So we're taking the cross product of those two, and that is our normal at that location. or that is a normal vector at that location. Of course, you could multiply by constants and it would still be normal to the surface, because multiplying a vector by a constant just changes the length, right? Unless we multiply by a negative constant, then it changes the length and it flips it, changes the direction as well. So we have 1, 0, -2, 0, 1, -2. Just evaluate that cross product. Cross out this row and this column. We have 0. Actually, I don't need to do this here. We'll have 0, whoops, minus a -2. It's +2. Cross out that row and that column, get a negative there. Then we have a -2 minus 0. Cross out this row and this column, and we have a 1 minus 0 there. So we get 2, 2, 1. Okay, small integers, that's great. That's our normal vector. Those are our components A, B, and C. And then if somebody asked you for the normal vector, we would be done. We answered that question. The normal vector to the surface at that point is 2, 2, 1. Now we were also asked to find the tangent plane. So we'll substitute x naught, y naught, z naught. That was that location that they gave us. So it's 1, 1, 2. And the normal vector with components A, B, C, which was 2, 2, 1, into the equation of a plane. And then we simplify. So we have A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. A, B, and C are 2, 2, and 1. X, y, and z are variables, so they're still there. And then x naught, y naught, and z naught are 1, 1, and 2. So that's our equation. It's just not simplified. So we distribute the 2's, distribute the 1, which doesn't do much. At least we lose the parentheses. And now we've got a -2 minus 2 minus 2. So if we can add that to the other side, we'll have a 6 over there. And that is the equation of the tangent plane. Okay, so I want to draw a little picture for you, just a little tiny picture. X equals 1, y equals 1, z equals 2. So that's this point on the surface. We got a little tangent plane there. And the normal to that plane has components 2, 2, 1. And again, the way we find the normal is we just compute the partials with respect to u and v. Substitute in u naught and v naught, which you had to find by setting the x, y, and z equal to the given x naught, y naught, and z naught and solving for u naught and v naught. Once you find those partials at that point, compute the cross product. That's the normal. And then you can just substitute the normal and x naught, y naught, z naught into the equation of a plane. Okay, one last thing for this video. I want to find the surface area of a parametric surface. Actually, if we can go back to this picture. Now, right here, we found a little tangent plane by doing this, but in a similar way, for every line where u is equal to a constant, I could draw a curve in the xy plane. So that was u equals u naught, but I could find a different curve for the next value of u, and then a different curve for the next value of u, and then another one for the next value of u, and so on. And then we could keep letting z equal constants. So z equals that constant, z equals that constant, z equals that constant, and we would get a grid like this. It's not exactly a grid. But you get the idea. As z goes through, or not z, as u goes through a range of values and v goes through a range of values, each of these little rectangles down here is associated with a little piece of the surface over here. If I want the surface area of that guy, well, I can take the partial of r with respect to v and the partial of r with respect to u, and those are going to be tangent to the surface. And then if I want the area of that little piece, it's approximately the area of the parallelogram that has those two partial derivatives at sides. So I've got this little parallelogram. I've got this part of the surface like this. Actually, that should be a vector. Vector is going to have a straight edge. This is the partial of v, or r with respect to v at u naught v naught. And this is the partial of r with respect to u, evaluated at u naught v naught. The area of that little piece is approximately the area of the parallelogram with the partial of r with respect to v and the partial of r with respect to u at u naught v naught as adjacent sides. And remember from that first chapter, if I want the area of a parallelogram with two vectors as adjacent sides, all I do is take the cross product and then take its magnitude, and that's the area of the parallelogram. So let me write that down. Surface area of one little piece of our surface. Oh, actually, that's not quite right. It's going to be the partial of r with respect to u at u naught v naught times delta v. And this is the partial of r with respect to u at u naught v naught times delta u. That's better. So we'll have the surface area is the magnitude of the cross product of these two vectors of course, this is evaluated at u naught v naught. And since delta u and delta v are scalars, and we'll assume that they're positive scalars, we can factor those out. That's the surface area of one of our little pieces. And that's at a particular UV, but if we evaluate this at the ith, that sort of ith jth rectangle, let's just evaluate them both at I. So I'll label them all with I's. Then the total surface area is the sum of a bunch of pieces that looks like this. And the surface area for a parametric surface is the double integral over d of the magnitude of that times dA in the UV plane, which is du dv or dv du. Now, this is a little different from that cross product that we just found in the last problem. In the last problem, when we found the cross product, we had already evaluated those two vectors at the point, and then we evaluated the cross product. Here, we want this to be a function of u and v so that we can integrate it with respect to u and v. We're going to have a slightly different area for each of those little parallelograms. It's going to depend where we're at on the surface. And D is a region in the UV plane. We're using R for the XY plane. We use D as our notation for the region in the UV plane. But this needs to be variable. It needs to depend on u and v. Then we'll compute the magnitude, that'll be our integrand, and then we'll evaluate the double integral. So let's look at this guy. Let's find the surface area for this guy right here. So we have R of u and v was u cosine of v times I hat plus u times j hat plus u sine of v times k hat. And u goes from 0 to 4, and v goes from 0 to pi. That's nice. We already have the bounds for d. They're stated for us. And we know that this represents part of a cone that lies above the xy plane. And it looks roughly like that. And we know it ends here at x or at y equals 4. Okay. The first thing I need to do is I need to compute those two partial derivatives and take their cross product. The partial of r with respect to u comes from taking each of those components and differentiating with respect to u. It's really not too bad. That's a constant times u. The derivative of a constant times u is just my constant. Derivative of u with respect to itself is 1. The derivative of a constant times u again is just the constant. Now I want the partial of r with respect to v, so I take the derivatives with respect to v, term by term. I keep saying term by term. Component by component. Derivative of cosine of v with respect to v is negative sine of v. And the u is a constant, so we bring that down. The derivative of u with respect to v, well, u is being treated as a constant, that's 0. And the derivative of a constant times sine of v with respect to v, so constant times the derivative of sine of v, which is cosine of v. So I've got those two. And what do we need? We need to compute the cross product and find its magnitude. This isn't so bad. It looks bad, but it isn't bad. In the first row, or in the second row here, we're going to have the components of the partial of r with respect to u. In the third row, we've got the components of the partial of r with respect to v. In that top row, we always have I hat, j hat, and k hat. Okay. So now we cross out this row and this column, we multiply across, and then we get u times cosine of v. And then we subtract this times this, that's 0. Then for j hat, you always subtract. So cross out that row and that column, put a minus there. Then you do this times this. I've got a cosine times cosine, so I'll have a u times cosine squared. Minus, I'm subtracting a negative, so that's going to be adding u times sine squared. Oh, that's nice. You guys see it? You see the simplification coming? I hope you do. Cross out that row and that column. Last thing we do is 0 minus this. We're subtracting a negative, so that's adding. And if you factor out a u from here, we get that. And look, we get cosine squared plus sine squared, same angle, so it's 1. Very nice. Nice and easy. Oops. So that's our x component. Our y component is just negative u, and our z component is u sine of v. Now that is the cross product, which would give us the normal vector at any uv value, any uv in that domain that they gave us. But we don't want the normal vector. What we want is the surface area, which turns out to be the magnitude of the normal. Actually makes sense if we think back to the fact that the magnitude of the cross product is the area of the parallelogram from that first chapter. That cross product gives us a normal vector. The area of the parallelogram gives us a surface area, approximately. I think that's pretty cool. So now we want to compute the magnitude of that vector. So we take the components, we square them, add them, and take the square root. So I'm substituting in my x value, my y value, and my z value. Square all the pieces separately. I've got 2 factors there, so square the first factor and square the second factor. You guys see it? You can factor out a u squared from everything. That's nice. Always like when that happens. Let's see what's left over. Got a cosine squared v plus 1 plus sine squared v. I know you see it. Sine squared plus cosine squared is 1, so we're going to have 1 plus 1 there. That's 2 times our u squared. And so that would be square root of 2 times the absolute value of u in general, but u is on the interval from 0 to 4. So u is positive. So we just get, or it's non-negative at least, so we get u. So that is our integrand. So now we can substitute into our surface area formula. And evaluate the integral. I've got the surface area, which is represented by capital S. I know it's a little bit odd that we're using capital S to represent the surface and also the surface area. That'll make more sense when we start integrating over surfaces shortly. So the surface area S is equal to the double integral over d of the magnitude of that cross product times du dv or dv du, either one is fine. And we're integrating from 0 to pi and 0 to 4. We've got the square root of 2 times u. These are bounds for u, so we integrate with respect to u first, then v. You could also do it the other way around because they're just constant bounds. And that's going to give you the surface area of this little piece that we found earlier. So we start on the inside and we work our way out. Square root of 2 is a constant. So we add 1 to the exponent, divide by the new exponent, substitute in u equals 0 and u equals 4, and subtract. At 4, we've got 16 divided by 2, which is 8. And at u equals 0, we get 0. Antiderivative of this constant with respect to v is that constant times v. We evaluate at 0 and pi and subtract. So we get 8 pi times the square root of 2. Square units. If you want a numerical approximation, you can use your calculator to find it. That's the surface area of this guy. It's that top half of a cone, or the top half of one nap of the cone. It's like there's always like that double napped cone. Here's like, one of them. We only took the top half, the part above the xy plane, and we have that part where y ranges from 0 to 4. That's its surface area. Okay, so let's briefly review everything we just talked about. Want to graph a parametric surface. The way you do it is you eliminate the parameters u and v. And the way that generally works is you solve the equations for u and v, and then you substitute into the other equations until you get rid of all the u's and v's and you just have x's, y's, and z's. Now, frequently we've got sine and cosine of the same angle. So we're going to use that Pythagorean identity, sine squared plus cosine squared is 1, a lot, in order to get rid of those angles. Once you do that, you're going to rearrange the equation of your surface until it looks like one of the quadric surfaces that we studied earlier this semester. To get a parametric representation of a surface given by f of x, y equals z, just replace your x with u, your y with v, and then let z be f of u and v. And that works exactly the same way if x is a function of y and z, or if y is a function of x and z. You just let the independent variables be your u and v, and then let the equation that was given to you determine the equation of the parametric equation for that other variable, that third dependent variable in the relation that you started with. To find the normal vector of a parametric surface, we did this. You take the partial of r with respect to u and the partial of r with respect to v. That's giving you slope in one direction and slope in another direction. So that gives you two tangent vectors. Well, you take the cross product of those two vectors to get a vector that's perpendicular to both of them. You evaluate it at u naught, v naught. That has components, 3 components. We'll call them a, b, and c. And you can use that to find the equation of the tangent plane. You need the point in the plane and the normal vector. And you just go to that plane equation that we studied at the very beginning of the semester. Now to find surface area, it's just this formula for a parametric surface. So you find the normal vector, and then you find its magnitude, and that magnitude times du dv, that's giving you a tiny surface area. It's the area of one of those little parallelograms. Then you want to add those up for all the parallelograms, which gives you this double integral. And usually the bounds for u and v are given to you, and you just integrate from the inside out. So that is our first lesson over parametric surfaces. The next lesson will involve surface integrals.